That's our repetition. 22nd lecture, and the lecture is on resonance. Last time I had started series resonance, that is a series RLC circuit which was excited by an AC generator with a variable frequency, and if I call this as the voltage phasor V, then the current phasor in the circuit is given by V over the complex impedance, and the impedance of the circuit is R plus J omega L minus 1 by omega C, which has a magnitude and a phase. The magnitude is square root of R squared plus omega L minus 1 by omega C whole squared, and the angle is tan inverse omega L minus 1 by omega C divided by R. And you see that if frequency is increased from 0 towards infinity, then the impedance starts with infinite value. At omega equal to 0 the impedance is infinite, and the angle at omega equal to 0 is simply tan inverse minus infinity, which is minus pi by 2. As omega is increased, there will be reached a point when omega L becomes equal to 1 by omega C, and under that condition the circuit shall be purely resistive, that is, imaginary part or the reactive part shall be 0, it will be purely resistive, and the impedance obviously shall be a minimum. The angle at that point when omega L is equal to 1 by omega C, obviously the angle is 0. As omega increases beyond this frequency, which we call the resonance frequency omega 0, which is 1 over square root of LC, beyond this frequency this term dominates, omega L becomes greater than 1 by omega C, so the circuit becomes inductive because its reactance is positive. The impedance again increases towards infinity. As omega goes to infinity, the impedance magnitude goes to infinity, and the angle goes to tan inverse infinity, which is pi by 2, and therefore if I draw a plot of the magnitude and phase, the magnitude goes like this. It starts from infinity, goes towards infinity, and attains a minimum value of capital R at omega equal to omega 0, and at this frequency if you plot the phase plus pi by 2 and minus pi by 2, if you plot the phase phi versus omega, then it starts from at omega equal to 0 the angle is minus pi by 2 and minus pi by 2, and it goes through 0 at omega 0 and goes to plus pi by 2 as omega goes to infinity. This frequency omega 0 is called the frequency of resonance, and resonance implies, the definition, formal definition of resonance is that the impedance or the admittance of the circuit becomes purely resistive, which means that the voltage and current at this frequency shall be in phase. If the circuit is purely resistive, the current and voltage shall have no phase difference between them. Another way of looking at resonance is that the admittance of the circuit mod Y shall show a peaking response, because admittance is the reciprocal of the impedance, and the maximum value of the admittance shall be equal to 1 by R, and this curve shall also change its sign, that is, it will start from plus pi by 2 and go towards minus pi by 2 as omega increases. This phenomenon, the phenomenon of resonance, under which the voltage and current in a circuit are in phase, this is the definition of resonance, can also be expressed in terms of current and voltage. suppose we have a current phasor I which is fed to the series combination of R, L and C, then the phasor diagram can be drawn with regard to, let the voltage be V, voltage phasor be V, then if this is the current phasor, if this is the current phasor I, then the drop, voltage drop across the resistance shall be IR, and this obviously is in phase with I. So if I call this VR, then with regard to VL and VC, you notice that VL is j omega Li, and therefore it leads the current phasor by 90 degrees, and therefore VL would be in this direction. Let us say VL, it will lead I by 90 degrees. On the other hand, the capacitor voltage across the capacitor Vc shall be I divided by j omega C. So it would be in the opposite direction. That means this will be the direction of V sub C, and depending on the frequency, whether the frequency is below resonance, above resonance or at resonance, the total voltage or the total voltage across the circuit V shall either lead the current or lag the current or be in phase with the current. For example, the picture that I have shown here is almost true for omega equal to omega 0. That means VL and VC are equal in magnitude and opposite in direction, so they cancel each other, and therefore the total voltage V under this condition shall be simply equal to VR, which is obviously in phase with the current phasor I. Suppose the situation was below resonance, that is omega less than omega 0. If omega is less than omega 0, then which of these two phasors will have a greater magnitude? Vc, and therefore the resulting voltage would have been Vc minus VL added to, vectorial added to VR, and therefore the resulting voltage would have some direction like this, and it would have lagged the current I. Similarly, if the frequency is above resonance, the voltage leads the current I, and the angle of lead or lag depends on the angle of the impedance Z, that is tan inverse omega L minus 1 by omega C divided by R. This is the story of series resonance. Now under series resonance, a very peculiar thing occurs, that if you consider VL equal to VL phasor as j omega L I, and let me take another VL phasor is j omega L I, this is in general true. Suppose we consider the situation at resonance, that is omega equal to omega 0. Under this condition, you know I is in phase with the voltage, and therefore I shall be equal to V by R. Under resonance, the impedance is purely resistive, therefore the current phasor is simply given by the ratio of the voltage phasor to resistance, and therefore VL phasor would be j omega 0 L, we are considering conditions at resonance, V divided by R, alright, which means that the magnitude of the voltage across the inductance is equal to omega 0 L by R, the magnitude of the voltage across the total circuit, alright. For example, if capital V is 1 volt, root mean squared value, because in phasors we are using RMS values, then VL can be 1 volt multiplied by omega 0 L by R, alright, and this quantity could be as large as infinity. Suppose we had no resistance in this circuit, suppose the resistance was 0. The resistance that we are talking of basically belongs to the inductance. You cannot make an inductance without a wear, and a physical wear shall always have a resistance, and therefore this resistance that we show usually is the resistance of the coil, or this resistance determines the merit of the coil. A coil from which we want only an inductance this is an inevitable nuisance, capital R. If we could make an ideal inductor, then obviously this quantity could become infinite, all right, and therefore capital R is a figure of merit of the coil, but not by itself. It is a figure of merit with respect to omega 0 L, that is the inductive reactance, and this quantity is usually denoted by Q. VL is Q times V, and Q can be very large. Getting a Q of 10 at high frequency is absolutely no problem, which means that you can get a stepping up of voltage without using a transformer, and sometimes this is also called a resonance transformer. That is, you are using the phenomenon of resonance to get a stepped up voltage, all right, Q times B. In a similar manner, if you had investigated the capacitor voltage V sub C at omega equal to omega 0, if you had investigated, you would have seen that V sub C is also equal to Q times V. Remember, we are considering only amplitudes, only magnitudes, all right. So at resonance, V sub C and V sub L can be much larger than the applied voltage, and so there is a stepping up, and this stepping up is technically known as resonance transformation. That is a transformer which uses the property of resonance. You must remember, however, that VL and VC, that they are individually Q times V, should not matter, because one is in opposite phase to the other. So the total voltage across the pure inductance and the capacitance is equal to 0. The total voltage is dropped only across resistance, and that is how the current in the circuit becomes capital V divided by R. Now, does that mean that if I plot, let's say if I measure the voltage across the capacitor V sub C by means of a voltmeter, a VTVM, and plot it versus omega, does it mean that it will show a response like this? Yes, the current is maximum at omega equal to omega 0, and therefore the capacitor voltage, the voltage across the capacitor, should show a curve like this, should show a variation like this. Similarly, voltage across the inductor. However, it can be very easily shown that the frequency of maximum voltage is not equal to omega 0. Omega m is not equal to omega 0. And the reason is not difficult to find. What is the reason? Reason is VL or V sub C. Let's consider VL. VL is omega L times V j omega L V divided by R. No, I beg your pardon. In general, it is Z. In general, all right. In general, the current phasor is V by Z, the impedance, and the voltage across the inductance is equal to j omega L, its impedance multiplied by the current. And therefore, if you take its magnitude and I omit a couple of steps, you can see that the magnitude would be omega L V divided by square root of R squared plus omega L minus 1 by omega C whole squared. Is that clear? I am taking the magnitude, so j I omit, omega L, magnitude of V is V, and magnitude of Z is this. And you see that omega occurs in the numerator and also in the denominator, and therefore VL is not necessarily maximum when the denominator, this term, becomes 0, because there is an omega here. In fact, to find out the frequency of maximum, what you have to do is dVL d omega shall be put equal to 0, and you can show that omega m, this I leave it to you as an exercise, you can show that omega m is equal to 1 by square root LC minus a quantity which depends on capital R, and I shall write down, as far as I remember, the expression is this, minus R squared by 2L squared, but I will put this with a question mark. You can you can verify or annul this claim, you can find out the correct expression. Similarly, for the voltage across the capacitor. Now, the circuit that we had considered was a series circuit, that is a resistance, inductance and a capacitance all connected in series, and the resistance, as I said, came from the coil, came from the inductance. We can also consider the dual circuit in which the three elements are connected in parallel, R, L and C, and then it would make sense to talk of a voltage excitation and find out the total current phasor in the circuit, and it will consist of three components, namely IR, IL and I sub C, and you can see that a similar phenomenon shall occur, a similar phenomenon like resonance shall occur, under which condition the reactance of the inductor shall be cancelled by the reactance of the capacitor. They are not in series now, and therefore what can be cancelled? Not reactance but susceptance. Susceptance of the inductor shall be cancelled by the susceptance of the capacitor. Well, this can be formally proceeded with exactly in the same manner as we did for the series resonance circuit, but you can see that the most appropriate thing to compute here is the admittance. All right. So Y of j omega, as you can see, is G is 1 by R, plus the admittance of the capacitor is j omega C, and the admittance of the inductor is j omega 1 by j omega L, and therefore L and C interchange their roles, and G takes the part of resistance in a series resonance circuit. This I can write as j omega C minus 1 by omega L, and one can proceed exactly similarly. That is, the magnitude of Y shall be square root of G squared plus omega C minus 1 by omega L whole squared, and the angle of Y shall be tan inverse omega C minus 1 by omega L divided by G. And once again you can see that when omega C is equal to omega L, that is when omega equals to omega 0 equal to 1 by square root LC. The susceptance of the capacitor, which is omega C, cancels the susceptance of the inductor, which is 1 by omega L, and the current and voltage, while the admittance angle would be 0, so the current and voltage shall be in phase. In the phasor diagram now, instead of taking I as the reference, we take V as the reference. All right. Then we argue that IR, the current in the resistance, must be in phase with V. So this is IR. IL phasor shall be V divided by j omega L, V divided by j omega L. So it would be lagging. This would be the direction of IL, and I sub C, the current phasor in the capacitor, shall be j omega C V. In other words, this would be leading the voltage or the current in the resistance by an angle 90. This will be I sub C, and the figure that I have drawn now is approximately, it represents resonance condition in which IL and I sub C are equal and opposite to each other, they cancel each other, and therefore the total current in the circuit is equal to the current in the resistor, which is simply the ratio of the voltage phasor to the resistance. And this resonance, because of the parallel connection of the elements, is called parallel resonance, as opposed to series resonance in a series connection of R, L and C. Can you tell me now what will happen if omega is less than omega 0? If omega is less than omega 0, then which current shall be higher length? IL, and therefore the total current shall be lagging the voltage. Similarly, if omega is greater than omega 0, then the total current shall lead the voltage. Okay. So series and parallel resonance are very similar phenomenon, and one should not be surprised to see the similarities, because one circuit is the dual of the other circuit. The role of series connection is taken over by parallel connection, the role of voltage is taken over by current, and the role of current is taken over by voltage. So however, there is an important distinction now, namely that if you have, let us say, this parallel resonance circuit, in a very similar manner, if this is the voltage phasor R, L and C, the current in, let us say, the inductor branch IL, the current in the inductor branch IL, or the current in the capacitor branch, you could take any, but let us take IL. The current in the inductor branch will be voltage phasor divided by j omega L, all right, and at resonance at omega equal to omega 0, the voltage phasor, the voltage is in phase with the total current I, and you know that IL bar shall be 1 by j omega L. This will be simply I phasor multiplied by R, because the circuit is at resonance. All right, at omega equal to omega 0, the current and voltage are in phase, and the voltage is simply current multiplied by the resistance, because the two currents IL and IC cancel each other. There are two currents IL and IC, but one is equal and opposite to the other, so they cancel each other. Now you notice that the magnitude, if we are talking simply of the magnitude, then this is R by omega L multiplied by I. R by omega naught L, yes, thank you, R by omega naught L times I. And you notice that this quantity, well, if I call this Q prime, let us say, some other quantity Q prime I, you see that at resonance the current in the inductor, in a similar manner you could argue the current in the capacitor also, can be multiplied by a constant Q prime, which could be as large as infinity. When is it infinity? If capital R is infinite, that means there is no resistance here, all right. The current can be infinitely large, and therefore I have denoted this by Q prime. However, this Q is not the same as the Q defined for series resonance. The two Qs are different, and the difference comes because the resistance here is in parallel with the inductor, whereas in the earlier case the resistance was in series with the inductor. For a parallel combination like this, it is, the Q is resistance divided by reactance. In a similar manner, one could show that Q prime is omega naught CR, resistance divided by reactance, all right. These are the same, as you can easily see, R by omega 0 L. The point that I am mentioning to you is that the definition of Q in the two cases are quite different. In one case it is reactance divided by resistance in the series case, in the parallel case it is resistance divided by reactance, and therefore it appears that if we wish to use the parameter Q to characterize the merit of an inductor or the lack of it, all right, then a more universal definition is needed, and this definition for any circuit, any inductor or capacitor is formally given in terms of energy, that is Q for quality, Q for quality or figure of merit. The quality of any reactance or energy storage element, which is either an inductor or a capacitor, is defined as twice pi multiplied by maximum energy stored divided by energy dissipated per cycle, well, which means that Q, the quality, has something to do with the energy storage capability of the element vis-a-vis the energy that is dissipated in every cycle, all right, and it is this ratio which is considered as the definition of Q, universal definition of Q. Now we can easily calculate this, for example, for a series RLC circuit. For a series RLC circuit, it's very easy to calculate. Suppose the current is root 2I, let's say cosine omega t. Suppose a current root 2I cosine omega t flows. Then what is the maximum energy stored? The maximum energy stored in the inductor, if you consider, it is half L maximum energy, maximum current is root 2I, therefore 2I squared, that is equal to Li squared. Is that okay? Maximum energy stored will be at the instant at which the current is a maximum, half Li squared, and energy dissipated per cycle would be Ri squared multiplied by per cycle. So Ri squared is the power energy per unit time. This should be multiplied by the time period, capital T, all right, and therefore Q for this circuit shall be twice pi Li squared divided by Ri squared. Now what is capital T? Capital T is 1 by frequency, and therefore 2 pi f, which obviously is omega L divided by R. This is the definition that we gave arbitrarily, that is a figure of merit, by considering the ratio of voltage across inductance to the applied voltage in a series resonance circuit. It comes out to be the same. However, it is conventional to define Q at the resonance frequency. In other words, Q, if you define at resonance frequency, it is omega 0 L by R, and from an exactly similar argument we could show that if C was associated with this resistance, well, then this is simply 1 by omega 0 CR. This also follows from the fact that omega 0 is 1 by square root LC, and therefore Q of an element is a very useful measure of the quality or the energy storage capability vis-a-vis, relative to the energy dissipation. Energy dissipation is a fact of life. It's an undesirable phenomenon, but it happens because you cannot make a resistance, you cannot make an inductance without a series resistance. Similarly, as you will see, you cannot make a capacitor without losses. Whatever the capacitor is, capacitor is simply two parallel plates, and in between there is an dielectric or an insulator. No insulator is perfect. Insulator is an insulator only approximately. It has a leakage, that is, it has a parallel conductance which accounts for losses, and therefore we talk of energy storage capability of a capacitor relative to its dissipation, and a Q factor characterizes this. In practice, it is very easy to make very high quality capacitors, but it is very difficult to make high quality inductors, and therefore resistance almost always in such circuits, series resonant or parallel resonant, is usually associated with the inductor, and we assume that the capacitor is almost perfect. All right. Now, because of the similarity between parallel resonance and series resonance, it appears that we should be able to find some kind of a universal expression which determines the resonance properties, either series or in parallel. And if we take the question of series resonance, you see Z equal to R plus J omega L minus 1 by omega C. This is Z of J omega at any frequency, and you know that at resonance Z of J omega 0, if I call this as Z0, is simply equal to R, and therefore if I could express the phenomenon of resonance in terms of dimensionless quantities, it would have been very welcome. That is, quantities which are independent of the actual values of resistance and actual values of capacitor and inductance. All right. So what we do is we divide Z0 by Z. Obviously then this ratio will be dimensionless, and you can see that this will be the same as admittance to the admittance at resonance, and you can express this as R divided by R plus J omega L minus 1 by omega C. All right. I shall repeat this expression here, Z0 by Z equal to R divided by R plus J omega L minus 1 by omega C, which I can write as 1. Now I divide by R. 1 divided by 1 plus J excuse me, omega L by R minus 1 over omega CR. All right. Now you see that omega L by R is also dimensionless. Isn't that right? This is in ohms, this is in ohms. Similarly, 1 by omega CR, 1 by omega C is in ohms, divide by R, so that is also dimensionless. It has to be, because you are adding one quantity to the other, they have to be of the same dimension. However, if you look at omega L by R, you can write this as omega by omega naught, all right, and multiply by omega naught L by R. Agreed? I have brought in, I have divided by omega 0, multiplied by omega 0, but you recognize that this quantity is simply the Q, and therefore I can write this as Q times omega by omega 0. In a similar manner, 1 by omega CR I can write as 1 by, well, I can write as omega 0 divided by omega, then 1 by omega 0 CR, and you notice that this is also equal to Q, 1 by omega 0 CR, because 1 by omega 0 C is omega 0 L, isn't that right? This is equal to omega 0 L. So this is also Q, therefore this is Q times omega 0 by omega, and therefore we get a universal form of expression for the for the dimensionless ratio of impedances. This is 1 by 1 plus J Q. From both of these terms I can take Q out, from both of these terms I can take Q out, and then I write omega by omega 0 minus omega 0 by omega. All right, I can do that. Now obviously this will have a maximum, this will have a maximum when omega by omega 0 equals to omega 0 by omega. That means when omega equal to omega 0, the maximum value is 1. This is independent of the actual values of resistance, inductance and capacitance, and in that sense it is a universal curve. The curve will go like this. When omega equal to 0, obviously the ratio would be 0, okay, because omega equal to 0, this makes it infinity, 1 by infinity is 0. When omega is infinite, it is also 0, and in between at omega equal to omega 0, well, it shows a maximum like this. This frequency is omega 0, this is omega, and what we are plotting is the dimensionless ratio of the two impedances. All right. This now becomes unity. All right, and it now makes sense. You see that this is the curve of a band pass filter, isn't it right? Band pass filter. So it now makes sense to talk about the bandwidth or the frequencies at which the impedance falls down to 1 by square root of 2. All right, let's call these frequencies as omega 1 and omega 2. Then the difference between omega 2 and omega 1 is defined as the bandwidth of the circuit, width of the band at which the impedance magnitude is no less than 70.7% of its maximum value. All right, we can actually find out omega 2 and omega 1. When when will this magnitude become equal to 1 by root 2? Obviously this quantity will have to be equal to plus 1 or minus 1. In either case it would be 1 by root 2, and therefore omega 1 and omega 2 satisfy the equation q omega by omega 0 minus omega 0 by omega would be equal to either plus 1 or minus 1. In each case it will give a quadratic equation, isn't that right? Whether it is plus 1 or minus 1 doesn't matter, it will give a quadratic equation, and therefore there shall be how many solutions to this equation? 4 of them. 2 will be negative and 2 will be positive. We accept only the positive solutions, and you can show that omega, you can show by actual calculation, I skipped the algebra, you can show that omega 2 1, that is first we take omega 2 the higher frequency, is equal to omega naught we have already defined, the resonance frequency 1 by square root LC, omega naught square root of 1 plus 1 by 4 q squared, q is omega naught L by R or 1 by omega naught CR, q has already occurred in this dimensionless form. So we find out in terms of q plus minus omega naught divided by 2q. All right, this is the expression, and if you notice the bandwidth is equal to omega 2 minus omega 1, therefore it is simply omega naught by q, and therefore the circuit q is can also be related to how good the circuit behaves as a band pass filter. You can see that small q is omega naught divided by omega 2 minus omega 1. All right. In other words, what does this mean? It means that higher the value of q, the narrower will be the bandwidth. So if you want a sharp resonance, for example, you want to pick up one particular station from all possible stations which are radiating upon your antenna, then your tuned circuit or the resonance circuit is also called tuned circuit, tuned, T-U-N-E-D, tuned circuit has to have a Q which is very large. A Q of the order of 10 in practice usually suffices. Now in this application we give this Q a separate name, we call it selectivity or circuit Q, as it is usually called, selectivity or circuit Q. And the reason that we have to distinguish between the two is as follows. You see, I can have an inductor, let's say L, and its associated resistance, let's say small r. All right. The Q of this combination is QL, let's say, is omega 0 L divided by small r. Now I want to tune this by using a capacitor, and perhaps if I do that, then the selectivity of the circuit, if I simply end the circuit here, then the selectivity of the circuit will be same as QL. All right. Suppose I want a greater bandwidth. Instead of a smaller bandwidth, I want a larger bandwidth. So what do? Connect a resistance. That's right. Connect an external resistance R. This will reduce the selectivity of the circuit, and reduction of selectivity means that I want a larger bandwidth. All right. So the Q or selectivity of the circuit now QC will now be different from QL. QC will be less than QL. In fact, QC will be omega 0 L divided by R plus small r, capital R plus small r. Is the point clear? The selectivity of a circuit, selectivity of a resonance circuit is not necessarily the Q of the coil. is not necessarily the Q of the coil, because there can be extra resistors in this circuit. All right? Yes.
Formulas for impedance and all that you gave in terms of Q.
Yeah.
Are these valid for any circuit?
Any circuit. Any circuit consisting of R, L and C. Parallel as well as series. In the parallel case, you will have to take the admittance. That is, what did we take here? Z0 by Z, isn't that what we took? In the case of series resonance. In the case of parallel resonance, we shall have to take Y0 divided by Y. If they are not series or parallel, yes, that's a good question. Then we shall have to start ab initio. We shall have to start from the roots. We cannot apply any of these formulas. But nevertheless, it can always be shown that whatever the complication of the circuit, if there is resonance, then around resonance it can always be described by a formula of the type 1 by 1 plus jq, the one that is shown. It can always be described by a formula of this type, that is 1 by 1 plus jq omega by omega 0 minus omega 0 by omega. Basic condition for resonance is the current and voltage are in phase. That's right. The phase difference between current and voltage are 0. This is defined as the condition for resonance. Alright. This is why the voltage maximum across an inductor is not necessarily at the resonance frequency. That is not a condition of resonance. Voltage maximum across a capacitor, it occurs at a slightly different frequency, slightly lower frequency, and that is not the condition of resonance. All right, but before we go to complicated circuits, let me mention to you some of the interesting features of these two frequencies on either side of resonance, at which the magnitude is 1 by root 2 of the maximum value omega 0 by 2q. By definition, the maximum is 1, and at these frequencies the value is 1 by root 2. This frequency is omega 0. All right. Now you notice a very interesting feature, that the product of omega 1 and omega 2, if you multiply the two, it's of the form a plus b times a minus b, so a squared minus b squared, and you can see that this is simply omega naught square. What does this mean? It means that omega 1 and omega 2 have geometric symmetry with respect to omega naught. Isn't that right? If omega 2 is 10 times omega naught, then omega 1 shall be 1/10 of omega naught. This is called geometric symmetry, and therefore this curve shall also be geometrically symmetrical. It does not have arithmetic symmetry. Is that clear? This curve of band pass filter does not have arithmetic symmetry. It is not that if you go equal distance on both sides you will get equal amplitude. No. You have to go according to geometric symmetry. If omega 2 is 10 times omega 0, then omega 1 shall be 0.1 omega 0. Alright. However, if q is large, suppose q is greater than equal to 10, let's say, then omega 2 1 would be equal to omega 0 square root of 1.0, this is 400, so 0.25, 0.0025. Is that clear? Plus minus omega 0 divided by 20. Agreed? And you see that square root of 1.0025, which is approximately 1.00125. Do you know these tricks? It is 1 plus delta to the power half, approximately equal to 1 plus delta by 2, and therefore this is approximately equal to omega naught plus minus omega naught by 2q, or 20, whatever it was, omega naught by 2q. All right. What does this mean now? It means that omega 2 and omega 1 are arithmetically symmetrical. Isn't that right? Omega 2 and omega 1 they are at equal distances, in general they have geometric symmetry, but if Q is large, then they have approximately arithmetic symmetry. Another way of saying this is that if in a high Q circuit, if you confine your attention to the region of band pass, then you can approximate it by arithmetic symmetry. Is the point clear? Arithmetic symmetry and geometric symmetry, they are facts of life, and one has to recognize them, appreciate them, and utilize them. We shall conclude this class with a couple of examples. One example, okay, and another a problem. One example and another a problem. The example is design and series RLC circuit for resonance at series RLC circuit. You have to design at resonance is required at 200 kiloradians per second, 200 kiloradian per second, and a bandwidth of 5 kiloradian per second. All right, resonance you want at 200 kiloradians, and the bandwidth omega 2 minus omega 1 has to be 5 kiloradians per second. The this an inductance of 2.5 millihenry and the Q of the inductance of 65 is available. All right, what is given to you is an inductance whose value is 2.5 millihenry. It has certain resistance. The resistance is not expressed directly, it is expressed in terms of Q, and Q is 65. Now, do you see that in this circuit, do you have to add a resistance? Yes, because the selectivity, as you can see from here, is 40, and therefore it has to be reduced from 65. In other words, you have to add a resistance. Now, how do you design this circuit? Design means L is given, you have to find out what additional resistance is required and what capacitance is required. Well, capacitance is very easy. Omega 0 is 1 by square root LC. Omega 0 is known, L is known, so you can find out C. How do you find the extra resistance? 65 is omega 0 L by R, and 40 is omega 0 L divided by R plus small r, and therefore from this you will have to find out capital R. Okay, one problem, and the other is a problem to be left with you. It's the problem that we had talked about in one of the classes when the lights went off. It is a complicated resonance circuit. It is a parallel resonance circuit in which L and C are in parallel, but unfortunately both of them have a series resistance of capital R, and in addition the elements have so conspired that L is equal to CR squared. You can see that the impedance, if you calculate in terms of S, it is simply R. We had discussed this, whether it is a transient, whether it is an exponential waveform, a battery, an AC, or whatever it is equal to R, and therefore there is no way to distinguish between this and a pure resistance R if they are enclosed within black boxes, black within inverted commas of electrical engineering, all right, in electrical engineering terminology. And this is one of the manifestations of resonance. Is this a resonance? Is this a case of resonance? Yes, because there is a reactive element, there is another reactive element, and the conspiracy is such, pure, but it's not at a single frequency. It's at all frequencies, and therefore this is all frequency resonance. It is not a single frequency resonance. Well, which means that in theory we can expect that there will be circuits which resonate at more than one frequency. For example, we can have circuits like this, all right, resonating at two different frequencies. This is also resonance. A minimum in the characteristic is also resonance. For example, it could be the plot of the impedance versus frequency. If it is the plot of impedance versus frequency, then what will you call these two resonances? The impedance is a maximum. These two must be corresponding to parallel or series. That's the question that I am asking. Parallel. In parallel resonance, the impedance maximizes, admittance minimizes, and this can be considered as due to a series resonance. All right, and and a simple circuit that one can think about is the following: a capacitor shunting a series resonance circuit, RLC. There will be a series resonance in this, and there will be a parallel resonance also, because the capacitor is shunting a reactive element. And this is the equivalent circuit of, have you heard of a crystal? Crystal oscillator. A crystal is the standard for frequency that you see at NPL or any other standard. The crystal oscillator, crystal, the equivalent circuit is this, which shows series resonance as well as parallel resonance. All right, we'll leave it at that. On Sunday we'll talk about general network analysis. Monday. I beg your pardon.